paper. So June 2016 paper, we did question 1 and 2. In question 3, in question 3, 6 students attempted to carry out a two-stage synthesis of a nitrobenzoic acid starting from ethyl benzoate. So two parts are there. The first part, ethyl benzoate, is hydrolyzed to benzoic acid. In the second part, benzoic acid is nitrated. So hydrolysis of ethyl benzoate, that is given how it is done. The first part, and the second part is the nitration is there for a benzoic acid. So student A followed the method exactly and obtained 0.021 moles of benzoic acid. Calculate the percentage yield. So percentage yield is a practical value divided by theoretical value into 100. And one mole of ethyl benzoate will give 1 mole of benzoic acid. So the simplest ratio is 1:1. So first what we will do, we have the volume of the ethyl benzoate and we have its density. So using the density and the volume, we'll find the mass, and from the mass we'll find the moles of ethyl benzoate, and from moles of ethyl benzoate we'll get the moles of benzoic acid, and the ratio between them is 1:1. So we will get the equal number of moles of benzoic acid, so it won't make difference. So first we have the volume and the density. So using a density and volume, we'll find the mass in gram. Density is gram per centimeter cube and volume is in cm cube. So we don't have to convert the unit. So density is mass divided by volume. So mass will be density into volume. Density is 1.05 and the volume is 6. So we'll get the mass of methyl benzoate, which will be ethyl benzoate, which is 6.3 grams. So after getting a mass, we need the moles. So how to get the moles? Moles equal mass in gram divided by molar mass. So the molar mass of this whole compound, which is ethyl benzoate, C6H5COO CH2CH3. So this is ethyl benzoate. The carbon are there 1, 2, 6 and 8. So it will be 12 multiplied by 8 plus 9, because this C is also there. So 12 multiplied by 9 plus oxygen is there 16 multiplied by 2 plus hydrogen is there 3, 4, 5 and 5, 10. So 1 multiplied by 10. So this will give us the total mass of ethyl benzoate, which will come out as 150. So 6.3 divided by 150, that is 0.042 moles. And after getting a moles of ethyl benzoate, the same number of moles of benzoic acid will be there, as the ratio between them is 1:1. So as the ratio is 1:1, we'll get the same number of moles, which will come out as 0.042. So this will be the moles of the reactant as well as moles of the product. And to get the percentage yield is a practical value divided by theoretical into 100. So practically, we are getting 0.021 and theoretically we should get 0.042. So the percentage yield, practical value divided by theoretical value into 100. So this will give us about 50% yield. Is it clear, this one discussion? The next part, a student B just dissolved 1 gram of a sodium hydroxide instead of 2 grams. This student carried out the experiment. Show by calculation that student B did not have an excess of sodium hydroxide. So we will use the ratio here. like the ratio of the moles, but before taking the ratio of the moles, we should get the mass of moles of sodium hydroxide. So moles equal mass in gram divided by molar mass. So mass in gram, uh, which is 2 gram, like example. No. So when we will simply take the ratio between them, like if a student use 1 gram instead of 2. So moles equal mass in gram divided by molar mass of sodium hydroxide, which is 40. So 1 divided by 40, this will be 0.025. And what is the simplest ratio between sodium ethyl benzoate and sodium hydroxide? Because the ratio will be 1:1. Why? As it will produce benzoic acid C6H5COOH, that is the benzoic acid, where it will mix with sodium hydroxide. So when they react with each other, the simplest ratio is 1:1. So it will produce sodium benzoate plus water will be there as a product. So as the ratio between them is 1:1, 0.025 moles of sodium hydroxide are used. So we will use these moles of sodium hydroxide and we'll compare with the moles of benzoic acid, because when we the previous part, when we calculated the moles of benzoic acid, which were 0.021 and moles of sodium hydroxide are 0.025. So you can clearly see the ratio between them is 1:1. So if we have 0.025 moles of sodium hydroxide, we should have same number of moles, but we have more benzoic acid than sodium hydroxide. So this shows that sodium hydroxide is not an excess. Then another student dissolved 10 gram of sodium hydroxide instead of 2. This student noticed the mistake and started the experiment again. Explain why student C did not like student C dissolved 10 gram instead of 2. This student noticed the mistake and started the experiment again. So explain why student C did not need to start again. So as you can see, for a student C, it is already taking a large or excess of sodium hydroxide. So even if he repeat the experiment with the same amount, he don't have to repeat the procedure because like student A was using 2 grams. So once 2 gram was used up, then for the second experiment, he has to add more sodium hydroxide. For student B, he's already taking a limited quantity of sodium hydroxide, so he should repeat the experiment. But for student C, already if he's taking 10 gram, 10 gram is more than enough. It's like too much quantity of sodium hydroxide. So even if he repeat with the same, it won't make a difference. That's why the answer here, sodium hydroxide is too much in the reaction mixture. So it does not make difference if we repeat with the same solution. Then student D decided to miss step 4 and 5. This student mass of a crystal was greater than the mass calculated mass obtained by student A. The benzoic acid obtained by student A had fewer impurities, benzoic acid obtained by compared to student D. Name the procedure described in step 4 and 5 and why benzoic acid prepared by student A was purer than student D. So when we check steps, step 4 and 5, step 4 and 5, what we did, here we filter it off like under a reduced pressure. So we'll have the crystals. Step 3, we'll have the crystal, but these crystals will have impurities, soluble impurities as well. So what we did, we dissolve the crystals into a minimum volume of a boiling water and then filter. So why we take a small quantity of a boiling water? Like these are the crystals with impurity. But student A did a recrystallization. Step 4 and 5 are actually steps of recrystallization. So what we do, we take a small quantity of a liquid, and this is small quantity of a liquid, we add the crystals and we dissolve them. Then we allow the crystals, then we allow the solution to cool down. So when we allow the solution to cool down, the crystals will form But this time when the crystals will form, it will be pure benzoic acid crystals as compared, because the soluble impurities remain in the solution. Here what it was having, it was having the crystal of benzoic acid as well as the impurity. But when we carry out a recrystallization, the soluble impurities, the impurities which are soluble, will remain dissolved, and when we recrystallize, we'll obtain the salt. So that's why recrystallization is always done to obtain a pure solute. So the step is known as a recrystallization. So that was the question, like what we call this step 3, 4, and 5. So we call them as recrystallization. Then student E decided not to carry out step 2, 3, 4, and 5. Instead, student E evaporated off water after step 1 and found 4.6 gram of crystals formed, which was more than the mass obtained by student A. One reason why student E obtained a greater mass than student A and give a structure formula for product. Look, if when we are the main reaction is we are doing hydrolysis of the benzoic ethyl benzoate. So this was ethyl benzoate, and when we are doing hydrolysis of the ethyl benzoate, this as a result, what it is producing, C6H5COOH, and it was reacting with sodium hydroxide, so C6H5COONA. And when we, so we are, this is a soluble substance, this is also a soluble substance. So what student E did after obtaining this, student E evaporated all of the liquid. So there was a liquid and student heated all of the liquid, so all of the liquid evaporate or escape. As a result, when all of the liquid evaporate or escape, what we are left behind? We are left behind with crystals. But then which crystals will be there? It will be a crystals of benzoic acid, and it will be crystal of sodium benzoate. Two different crystals will be there. That's why the mass obtained by student E is much higher than mass obtained by student A. Student A, because he was using a recrystallization, so most of the crystals which were formed are benzoic acid. Is it clear, this part? Student F ran out of time and filtered the solution in step 5 before it has cooled. A low yield is obtained. Why student F failure to cool solution result in a low yield? Because if we don't cool the solution, most of the substance will remain dissolved. Most of the solute will remain dissolved. That's why he will get a small amount of crystals. Then part 2, nitration of a benzoic acid is done. So we have a benzoic acid and nitration is done. Part F means like when a student is filtering off, because of lack of time, when student was filtering it off, student did not like this solution. We should allow the solution to cool down, because when the solution cool down, the solubility decrease and the crystals will start to appear, and then we will filter it off so that the solute left on the filter paper and the residue will be there on the filter paper and the filtrate will pass through. But instead of waiting for, because of student F run out of time, so student F did not cool down the solution. So if student F did not cool down the solution, so if the solution is hot, most of the solute is dissolved and very small amount of solute is crystallized. So when he will carry out the filtration, a small amount of crystals will be there on the filter paper. That's why he will get a low yield or smaller amount of product. So solubility changes as we change the temperature. So P, Q, and R are different compounds, the nitrobenzene. A student measure a melting temperature of a student may measure the melting temperature range of one of the separated product in sample 1. A student then recrystallized and took the melting point of sample 2. The student results are shown. Sample 1, the melting range is for the melting range before the recrystallization was 136 and 140. But after recrystallization, it is 144 and 146. The melting temperature of 3 structural isomers are given. P is there, Q is there, and R is there. We have to determine why are the temperature of sample A and B are different. So what is the reason why the melting temperatures are different for a substance? Because the melting temperature depends on amount of impure, like how much impurities are there. So they contain different amount of impurities. They have different purity level. That's why they have a different melting and boiling points. Then the last part, we have to identify, suggest which isomer is present in the sample. So which one is present in the sample? So when we check, this is 148, 142, and 241. First, R cannot be. Why R cannot be? Because R is having a melting point of 241, but these temperatures are not for R. So it cannot be R. So either P can be there or Q can be there. So when you check the melting point for P, it is 148, the pure P, and the melting point for Q, it is 142. So basically, whenever impurities are there, impurities lower the melting point. That is the effect. What is the effect of impurity on the melting and boiling point? If a substance is impure substance, they will have low melting point. And impure substance will have high boiling point. So boiling point increase and the melting point decrease compared to the pure substance. So when we compare this was a before recrystallization, so this was impure. So if a substance is impure, what is the effect of impurity? Impurity lower the melting point. And you can clearly see even when recrystallization is done, recrystallization does not completely make 100% pure sample. Still, the sample will be impure, but percentage of the impurity will be less. Like this is having a higher percentage of impurity, this is having a lower percentage, but both are impure substances. So whenever substance is impure, the melting point of a substance should be lower than the melting point of a pure substance. So when we check P, so this range 136 and 142, it is less than the melting point of pure substance. 144 and 146, this is also less than the melting point of a pure substance. So that's why the 2-nitrobenzoic acid P is the right answer. Why not Q? Because you can see 142 is there. This pure substance, pure Q, is having a melting point of 142. But this temperature, okay, this is one less than 142, but this is more than 142. So it means it is not substance Q, because whenever impure substances are there, the melting point is always lower than the pure substance. The next part, can the number of the peaks in low resolution NMR spectroscopy used to distinguish between P, Q, and R? So we have to check. Low resolution only gives the number of hydrogen environment. It does not give anything about the neighbors. So when we check number of the peak, this is 1. when we draw the structure, like this is C double bonded with O and OH, carbon, 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 and carbon. This will have NO. This will have H. 1, 2, 3, 4. So when we check the number of the hydrogen environments, how many hydrogen environments are there? This is one hydrogen environment. This is second hydrogen environment. Because they're different, like this is next, third, fourth, and 5 hydrogen environments. For P, 5 hydrogen. When we check for this one, 1, 2, 3, 4, 5 hydrogen. So P and Q will have 5 hydrogen environments. So they will in a high resolution, yes, it can be, but low resolution, because low resolution only gives the number of the hydrogen environment. So as they have the same number of hydrogen environment, we cannot distinguish P and Q. We can distinguish R because this is one hydrogen environment. These two are identical. So this is the second hydrogen environment. Like I can say this is A, this one is B, and this one is C. So R is having 3 hydrogen environments. P will have P and Q will have 5, 5. So they will have the equal number of hydrogen in the environments. So we cannot distinguish P and Q. We can distinguish PQ with R, but we cannot distinguish Q and R in the low resolution NMR. Is it clear? Then the number of that we did in a mass spectrum, the mass to charge could be used to confirm the only nitration occur in this reaction. So in the mass spectrum, the mass to charge value could be used that mononitration. Mononitration means only one nitro group is attached. Or one, like if multiple nitration is there. So which fragment can be used that mononitration is done? Like we can just take the total mass of this one. We will take the total mass of the whole this one divided by the charge, which is +1, because all of them will have the same mass to charge ratio. So mononitration, because mononitration is done, they all will have a same molecular mass. If multiple, like if here mononitration means one nitro group is attached, but if dinitration is there, 2 nitro groups are attached. Trinitration, 3 nitro groups are attached. So number of the nitro groups attached will change. So the mass to charge ratio will also change. So we just have to find mass to charge ratio of one molecule, and all will give that peak, the molecular ion peak. In question 4, vanadium is a transition metal and forms ion which has oxidation of +2, +3, +4, and +5. 2 students want to make a solution containing an ion in which vanadium has oxidation number of +3 and +4. Both students started with ammonium vanadate 5. The first student decided to make an aqueous solution containing vanadium 3. First, the student heat the solid ammonium vanadate 5 to make vanadium 5 oxide and write a balance equation for decomposition of ammonium vanadate, and state symbols are not required. So we want to prepare this ammonia and vanadium 5 oxide, which is V2O5, by the thermal decomposition of ammonium vanadate 5. So the balance equation, the equation will be NH4, ammonium vanadate is there. It is NH4VO3 decomposed into vanadium pentoxide plus ammonia, and steam is there, so H2O. Then we'll balance the equation. So we'll put 2 here and we'll put 2, all are balanced. How student confirm that the decomposition is complete? Whenever you want to make sure that the decomposition is complete, what we do, we heat the substance to a constant mass. What does it mean? We'll supply the heat energy, then remove the heat source, and we measure the mass of a substance. Then we supply the heat energy and again measure the mass of substance. Supply heat energy, again measure the mass of substance. How we will make sure that all of the substance has decomposed? So to make sure all substance decompose, we will re-weight. So when we will re-weight again, we will weight it again and we'll find the mass of a substance. If a mass is not changing, it means that the substance here, if the mass is not changing, it means that decomposition is completed and a substance does not decompose. Like it's stable now. Is it clear this part? So this is always the case when we are finding the water crystallization. So we always heat the substance to a constant mass. The student then reduce the vanadium 5 oxide to vanadium 3 oxide by passing hydrogen over a heated oxide. Identify hazard associated. Basically, hydrogen is a flammable gas. So hydrogen is flammable. It may catch fire. That is the one hazard of this technique. Then the student reacted 1.498 grams of vanadium 3 oxide with an excess of sulfuric acid to make 250 cm cube solution containing aqueous vanadium 3. Calculate the concentration for vanadium 3 in the solution. So moles equal mass in gram divided by molar mass. So first we'll find the moles, and how to first we'll find the moles of vanadium 3 oxide. And vanadium 3 oxide, what are the ions it will decompose? It will decompose into two vanadium ions and 3 oxide ions. So first we'll get the moles of vanadium 3 oxide, and then we'll use a ratio to get the moles of vanadium, and moles divided by volume will get the concentration. So 1.498 divided by the molar mass of vanadium pentoxide, that will use a periodic table. It will be 100. You have to use the periodic table 149.8. So it will give us 0.01, and then we'll use the ratio 1:2 is the ratio. So X cross multiply will get 0.02 moles, and moles divided by volume will get the concentration, but the volume should be in decimeter cube. So it will be 25 divided by 1000. So 250 divided by 1000. So 0.25. This will give us 0.08 moles per decimeter cube. Give the formula of two ions that would be present in high concentration in solution T, apart from vanadium 3 ion. So other than vanadium 3 ions, what are the ions present in the solution? The common oxidation states of vanadium are there. So as you can see in the question, they already mentioned that we are using a sulfuric acid, excess of sulfuric acid. So the formula of two ions that could be present in high concentration in solution T. So it contains sulfuric acid, so hydrogen ions will be there and sulfate ions will be there. Is it clear? Part C. Then these are the electrode potentials are given as well. Conversion. Uh, Here you can see vanadium. These data suggest that the stepwise reduction of acidified solution of VO2 using a sulfur dioxide was initially produced VO2 plus and then V3 plus. By calculation of reaction predict which will occur and show which stepwise reduction possible. Like first best thing is to identify the change in oxidation number for like what are the changes, what will happen. Ammonium vanadate in dilute sulfuric acid, the solution contain VO2 with a charge +1. So each oxygen is -2, two oxygen will be -4, so vanadium is +5. So this substance, vanadium is +5, and VO with a charge 2 plus, each oxygen is -2, so vanadium should be +4. So this is +5 and +4. And here this is +4 and change to +3. Now, how to work out, like we are using sulfur dioxide. Here we are using a sulfur dioxide. So if we check, like if we have vanadium 5 and vanadium sulfur dioxide. So the one which is having a higher electrode potential, reduction happen. So for this one, reduction happen, and the other one, oxidation happen. So this will be reduced and this will be oxidized. So the first case, the vanadium 5 will convert into vanadium 4. That is the first step. And then further what will happen? If we want to check, and what will be the total electrode potential of a cell? Electrode potential of a cell is reduction minus oxidation, redox. So when the equation 1 and 2 and 3 are there, so first the reaction will be there between equation 1 and 3. For equation 1, reduction happen, so it will be same. And what will the electrode potential of a cell? That is reduction minus oxidation. Reduction is potential is 1 and oxidation is 0.17. So we'll get the voltage of a cell that will come out plus 0.83. So it means this is the one. And then what will happen? There will be a reaction between 2 and 3. So vanadium 4 will convert it to vanadium 3. So how to identify which one oxidation happened? The one again, which one reduction happened? The one which is higher potential, reduction happened. So the electrode potential of a cell will be 0.34 minus the oxidation 0.17. So it will be 0.17 volts. So both will be a positive answers. Both are giving a positive answer. So it means that both reactions are feasible. First, 5 will convert into 4 and 4 will convert into 3. Is it clear, this part? When student bubble sulfur dioxide into a solution contain acidified vanadium oxidation number 5 convert to 4 are obtained rather than 3. Suggest why VO plus 2 ions are produced rather than, like when student bubble, vanadium 5 converting to vanadium 3, and then when according to the calculation, vanadium 4 will convert into vanadium 5 convert to 4 and 4 should convert into 3. But practically it does not happen. So what might be the reason? Remember, whenever we have electrode potentials, the electrode potential of a cell, if we are getting a positive answer, it means the reaction is feasible. But it does not give the tendency of a reaction. Maybe some of the reactions are having a very high activation energy. So that may not be possible for a reaction to occur at that specific condition. So even though the electrode potential of a cell is positive, but the reaction is not does not occur, this gives an idea that the activation energy of a reaction is high. And construct the overall equation for a reduction of VO 5 to 4 by sulfur dioxide. So how we construct? So simple way to construct the equation from the electrode potential. So this reduction happens because we want to construct between 1 and 3. And this one oxidation happens. The one which reduction happens, that will be as it is because these are always reduction potentials. But one which oxidation happen will be opposite, like this side will be, when we are writing, this side will be a reactant, this will be product. But here this is reactant and product. So when we combine the equation, it is VO2 plus 2 protons plus sulfur dioxide plus 2 water molecules gives BO plus 2 plus H2O plus sulfate ion plus 4 protons plus 2 electrons. And when we are constructing an equation, the number of electron lost by one should be equal to number of electron gained by the other. So because if this is like here in this equation, it is taking 2 electron, this is 1 only. So we have to first multiply both of them by 2. Because the number of the electron lost by one should be equal to the number of electron gained by the other. Electrode potential will not change, we'll just change the number of electron lost or gained. So what we will do, we'll multiply this equation. The first equation by 2, so this will be 2, this will be 4, this will be 2, this will be 2, and this will be 2. So here this is 2, this is 4, and what else? 2 electrons here, 2 electrons here, and 2 water molecules. Then we cancel out the common ion, H2O here, H2O 4H, 4H, 2 electron, 2 electron. So what we are left with? We are left with 2O2 plus sulfur dioxide gives VO plus 2 plus SO 4 minus 2. So this is the equation, a balance equation for, this was 2 here and 2 because the equation must be balanced. So this is a balance equation for the reaction in which the vanadium 5 convert to vanadium 4. Last part, having made solution of vanadium 5 and vanadium 4 and 3, a student decided to measure the standard cell voltage, vanadium 4 and 3 and aluminum 3 to aluminum. The student set up the apparatus to measure at 25 degrees centigrade high resistance voltmeter aluminum and vanadium. A concentration is also shown for vanadium 4 and hydrogen ions are there, and solution 1 mole per dm cube. Now what are the mistakes and platinum wire? So first thing, this wire which is used as a salt bridge, it should not be platinum, it should be made up of filter paper or tissue paper, you can say, which is soaked in salt solution. The second mistake student did, look, for vanadium there is only change in oxidation number. It's not producing a vanadium metal. So if the vanadium metal is not produced, it means student should not take this electrode as vanadium. It should be an inert electrode such as platinum. And the third mistake, 1 mole per dm cube of aluminum sulfate. So if we have 1 mole per dm cube of aluminum sulfate, when this substance will dissolve, it will give 2 aluminum ion and it will give 3 sulfate ion. So the ratio of aluminum sulfate molecule to aluminum ion is 1:2. So if the concentration is 1 mole per dm cube, the concentration of with aluminum ion will be 2 moles per dm cube. So it won't be correct. Why it won't be correct? Because whenever we are measuring the standard electrode potential, the voltage, the concentration of an ion in the solution should be 1 mole per dm cube, not 2 mole per dm cube. So these are the 3 mistakes in this setup. Is it clear? So he should take half mole per dm cube, like aluminum sulfate when he is modifying, he should not take 1 mole per dm cube, he should take half mole per dm cube, because half mole per dm cube give 1 mole per dm cube of aluminium ion. So this was the last question from June 2016, Unit 6.